All right. So I'm Yawar Siddiqui, and I'm a research scientist with the Surreal team at Reality Labs Meta. And I'll be talking about our work Shaper, upcoming work Shaper, that's about robust conditional shape generation from casual captures that we worked on with my colleagues. So let's start by motivating the problem a bit. As James was showing before, with the Aria glasses on, when I walk around with my apartment, we can get different kinds of signals. You can see on the right that I can track where I am in the apartment, and with the machine perception services, I also get kind of like the sense of 3D space around me with these semi-dense point clouds. Given these slam points and the visual inputs, we can get a pretty good understanding of the scene around me. If you run some off-the-shelf 3D instance detection methods, such as the egocentric volume lifting or ImVoxelNet or 3D EDR. So the sparse slam points combined with 3D instance information now give a good understanding of the scene, right? However, for downstream tasks that need physical interaction, this information in terms of geometry might be too sparse. For that, you also already have solutions such as, again, egocentric volume lifting that can reconstruct 3D surfaces of this scene. Even from like the trajectory we saw before was kind of a casual capture. It's not a scanning trajectory. But with EVL, you can get some good estimate of the geometry. One issue with these geometries that you get with these kind of methods is that everything in the scene is the same mesh. It's a single monolithic mesh. So you see here the TV, the furniture is all fused into the same thing. And yeah, it's like everything is carved from a single stone, right? Because of this, these meshes cannot physically interact with anything else, right? So for example, if you throw a boulder on this, it won't interact as you would expect because it's all the same mesh. And also, objects here are incomplete, right? So if I were to segment out this sofa and then like just move around it, I won't see the rest of it, right? Because these methods don't have the generative priors to complete these meshes. Another issue with this monolithic scene reconstruction is the fact that usually you are tied with a fixed resolution budget for the entire scene. This means that for individual objects, you're going to share that budget. And this means that these might not get enough detail. So as you see here, the lamp, the chair, and the table, they don't quite get details like the chairs don't have slits in them or the table is kind of really blobby. So to this end, we introduce Shaper. And let me pause here. So this is a new method, and it does object-centric 3D reconstruction. And for each of the detected objects that you saw from EVL, it would extract out post-image crops of the object that we're reconstructing. We'll have the slam points for that object. We'll also have a machine-generated caption, the couch with pillows here, and some mask prompts. And for this, from these inputs, what this method can do is, let's play this, complete the, generate a 3D reconstruction for the entire shape. And this you can do for each of the objects in the scene. You do it for each of them, get the same input for each of them, and run it. And what you get out is an object-centric reconstruction of your entire scene. Now, this approach to 3D scene reconstruction solves some of the issues we mentioned before, right? Like, so since each of these objects are individually reconstructed, they will move individually. They also get enough detail for each of these shapes, so you get a more faithful reconstruction of the shapes, right? So like you see that the table has enough detail, the couch has enough detail, the chairs have the slits in them, and now, so since you're doing it object per object, you get this detail out. And also, as I mentioned, like it's now a compositional object-centric reconstruction rather than monolithic, so physical interactions can be now simulated more plausibly. Now, Shaper builds upon the progress of image to 3D generative models, so we should talk a little bit about them. In the last 2 years, image to 3D has become exceedingly good. We've gone from class-specific models. There was days where we could only reconstruct chairs and tables. Like we would train one model that would reconstruct chairs, you'll train one model that will reconstruct tables. Now you have models that can go from any picture of any object to a 3D, like a really faithful 3D reconstruction. I would even say that at this point, conditional 3D generation to this limited case is close to solved. And people have started moving to harder tasks, right? Like, so in the lower right, you see Bang, which moves on to the task of part-based reconstruction now, not just the object. You have methods that move on to articulated object reconstruction. However, I would say that this statement, while true, there's a qualifier here. These methods can only work good for very clean, very clear, unoccluded, segmentable inputs. When you have something real, like what's shown here, right? In the real world, when you move around, you'll see a lot of occlusion, objects behind other objects, and like a lot of these methods segment out the object in consideration before they run the algorithm. If you run segmentation on these kind of inputs, even manually doing it, you might not get the whole shape because it's occluded. If you run something like SAM, even if you click a lot, you won't get like very good segmentations. And then again, like some objects are just maybe not noticed by too closely or may have too much sensor noise. And in effect, what you have is the reconstruction with these algorithms are not so ideal as we saw before. Here are some more examples of the scene that we saw before. And you see that like if the object is occluded a little bit, it will get cropped, or you have some artifacts as seen in this chair here. So in Shaper, we were exploring how to make object generation robust when input comes from more casual in the wild setting. So let's go step by step of what Shaper is, right? Like, so from the very basics, Shaper is simply a diffusion or flow matching model that uses a transformer denoiser that works in some latent space. So much like any denoising transformer, it runs not on the raw shape, but on some latent space. The latent space we use is a vec-set representation, and this is very common in like state-of-the-art 3D generation approaches. Next, we want to have some sort of control of what we're reconstructing, and this is why we condition on multi-view images of the objects that we observe. So we extract out Dino V2 features and embed them with plucker arrays to give a sense of where these images are coming from. And these stream of tokens then go to the transformer where they can be attended to. However, if you just do that, that's not enough. What we see is like, it works sometimes, but sometimes you see these kind of inputs which are less than ideal. Here's another example. Now, one thing that really helped, we found that if you condition additionally on the slam points, this increases the robustness a lot. So here I extract out some features with a sparse 3D ResNet and pass those tokens on as well to the transformer apart from the image tokens. And yeah, this gives significant improvements. So for the shapes that I showed before, on the left you see without points, on the right you see with points. And this improves the quality of the shapes a lot. However, we noticed that in cases where, one more thing I need to mention here is once you do this kind of SLAM conditioning, like other approaches, what they would do is like they would segment out these images before they reconstruct. With slam points, you don't need to do that. So you can, the network can figure out from the points and their correlation with the images which object you're trying to reconstruct. So you pass on the images with the background here. However, we noticed that there are cases where the network would sometimes reconstruct part of the objects which are very close to mesh. So here, I don't know if you can clearly see, but the bench is very close to the table. And when you're trying to reconstruct the bench here, the part of the table gets reconstructed. And here's another example where the cutting board is very close to the kitchen roll, and that also kind of gets reconstructed here. So to make it a little bit more robust, we find that if we take the points from the images, project them to 2D, and use them to prompt the Dino features, this kind of resolves the issue here. So the intuition here is that Dino features have enough information, right, to segment out the object. They already know like what different objects are represented by different Dino features. However, you still need to tell the model which is the object we're trying to reconstruct. And that's what the points do. They kind of prompt the Nino features like, this is the thing I want to be reconstructing. And this solves this issue of extra objects being reconstructed here on the right. Lastly, one more modality we leverage is machine-generated captions that can guide the denoising process. So the idea here is like all the other modalities we talked about, the images, the slam points, they can be incomplete, right? Like images can be hidden by other, like the object can be hidden by other objects in an image. Slam points might be incomplete, but text is always complete by definition, right? Like if it's a table, it's a table. There's nothing more to be described in terms of completeness. So that kind of guides the process a little bit more. However, doing all this multimodality, the model is not robust enough, and we still see cases where you get less than ideal reconstructions. So what we do is we make a lot of augmentations on all the modalities. So on the image side, we have a lot of object background augmentation, some foreground background augmentations, sensor noise augmentations. On the point cloud side, we have a lot of augmentations in terms of simulating partial observations, different kind of dropouts to simulate half point clouds, adding some structured noise. And one important thing we found here is that when you want to do these augmentations, you want to do it in the data loader. So you want to be able to do this on the fly and not like just process them and store them in the on your disk, right? Because what you want is like kind of an infinite data generation, basically. And when you do all these augmentations, this helps a lot. So you see there, like if you turn off any of these augmentations, you don't quite get the effect when you have both of them. However, this is still not enough. And the thing is, if you train with only large-scale object-centric data on the left, shown here on the left, these are great. These data sets are like diverse. There are millions of objects. You kind of learn objectness with this. But even after all these augmentations, they are very synthetic, right? Like that's very made up, right? Like all the augmentations that you're going to do are going to only replicate how real life would be. So to make a change to that, we do a second stage of training with much more realistic inputs from ARIA synthetic environments dataset. So we go over the whole dataset, we extract out crops for objects, and these are much more realistic. You get much more realistic occlusions, you have better point clouds on how you'd see in real life, and this also helps a lot. So with this in place, now you have a method that can like reconstruct real life things like chairs on the tables and tables with chairs around them. Yeah. And this kind of is what the method is. It's a rectified flow matching transformer working with a vec-set latent space, conditioned on multi-view images, slam points, 2D point tracks, and machine-generated captions. You train this with a lot of augmentation, which is on the fly for each of the modalities, and you have a two-stage curriculum training that makes for effective generalization. Now, how do you evaluate such a data set, right? Such a method. So there are many object data sets in the wild. There's DTC, which captures, which has a little bit of a control setup, right? Like you have an object placed on a table and the user goes around it. So it's not quite the casual setup we're looking for. The good thing about DTC though is like it gives complete objects. So we can evaluate against a good ground truth. On the other hand, ScanNet is very casual. You have captures of objects on how they would occur in real life, right? Like you have chairs and tables, it's a mess, right? Like it's how real life is. However, the ground truth geometry in these cases is very bad, right? Like it comes from a scanner, it's going to be incomplete. You don't want to benchmark your method that produces a full shape against this. So to this end, we also introduce a Shaper object evaluation dataset that has 178 object sequences across 7 scenes, and each of them are individually complete objects. And yeah, they cover a wide range of categories like tables, chairs, also small objects like lamps or devices, artworks, and so on. So we compare our method against multi-view to 3D. We find that compared to the EVL model or even Foundation Stereo running on Nebula on ARIA Gen 2, it's much robust compared to methods such as LRM, LIRM, DP-Recon. Our method is much more robust. Compared to image to 3D approaches that we build upon, even when you give like a really manually selected, really nice view with segmented manually with SAM, we perform much more better since we are much more robust to real world cases. Finally, compared to image to scene methods, which can take single or multiple images, we find that these approaches struggle in terms of placement of objects and their relative sizes, like shown in the middle 2 rows, while we can do a much better job with this. Just like any other method, like this, of course, has the limitations. When the sensor resolution is too low, the objects are too small, we struggle with the details. And sometimes you see in the model, you tend to reconstruct more than what the object is. So here in the input observation, ideally what you'd want is reconstruction of the table for the box that detects table and rest reconstructed individually, but sometimes we reconstruct more than that is. And one more fundamental limitation here is that since we're dependent on instances from another method, if those are missing, we're not gonna reconstruct those. So just as a quick recap, this is Shaper, and it's an upcoming method. It's coming soon on the website. And in the talk, we highlighted the need for object-centric reconstruction and the problems with generation in the wild. And we introduced a method for conditional object generation using multimodal conditioning with heavy streaming augmentations and curriculum learning. And we also introduced a dataset for in the wild object reconstruction evaluation. Thank you.